Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I think we'll get started. My name is Kwan-san Wang. Today I have this honor to host my former intern, Antoine, to interview with us. So Antoine interned with me probably 2 years ago, and he did such a good job that I cannot resist to bring him back for interview now that he's graduating. So today he is going to tell us that what he has been doing for his PhD thesis. So without further ado, yeah.
Hi. Is this working? Yes? You can hear me? Okay, so good morning, everyone. So as Kwan-san said, I'm Antoine Rowe. I'm finishing my PhD at Carnegie Mellon, and I'll be talking about my thesis topic, which is turn-taking, meaning conversational turn-taking as a dynamic decision process. So my general field of research is in spoken dialogue systems. So, well, let's jump right into it. So what current dialogue systems, what do they do? There's been lots of research on dialogue systems for the past maybe 2 decades at least now. And lots of research has been done on making them more robust, or able to ground information, able to deal with more complex structured information, etc. So that leads us to something like this. This is something that could be stated a state-of-the-art dialogue system, I guess.
What can I do for you?
When is the next 54C coming to 18th Street?
The 54C. Did I get that right?
Yes.
Okay. Where do you want to go?
Carson.
Going to Carson. Is this correct?
Yes.
Okay. Let me check that for you.
Okay, so by many accounts, of course, dialogue continues with the system providing results. By many accounts, this is a very successful dialogue. I mean, the person is getting their information without any problem. There's just 2 confirmations to make sure the information is right, but that's really not a big deal. However, I would say this is still far. So as you've understood, this is a system that provides bus schedule for people. And now let's listen to a recording of a very similar conversation with a human. That's an actual recording from a call to the customer service of the bus company in Pittsburgh. And let's see what that sounds like.
Thank you for calling Port Authority. How may I help you?
Yes, could you tell me what time the next 261Cs arrive downtown, going towards just outside?
51C?
Yes.
Let me get that for you. We have one leaving town at 3:30 and again at 4 o'clock.
3:30 and what else?
4 o'clock.
Okay, thank you.
Have a good day.
Okay, so there's still some difference here. We're not quite there yet, as you can see. And it's not a matter of speech recognition accuracy or even speech recognition speed, because that's not where the problem lies here. In this particular example, there are dialogues with problems in speech recognition, to be sure, but in this example, we do have now lots of dialogues that go well as far as understanding goes. Now, what are the differences between these 2 dialogues? One was a specific problem in prompt design, or difference in prompt design, where the prompts or the questions from the human operator tend to be much shorter, much more efficient than the ones in the system side. But that's not a very hard problem to solve at first sight, right? You just design your prompts to be short, and you're good. Now, the problem with this is that if you're using recorded prompts, that's probably fine. If you're using synthesizing very short utterances like 51C, you need to convey the meaning right, you need to use prosody in the right way. And humans are very good at that. That's why he's able to have to do it in this call. It's not that trivial to produce in synthesis. It's actually not really solved yet, I see. That's one of the big challenges of speech synthesis, having conversational prosody. The human is using it both in the confirmation here. Also, when he provides result, he's pretty good at emphasizing the important bits of information in his utterance so that the user gets it. And that allows, by the way, the human to speak very fast most of the time, much faster than the speech synthesizer does, because it can emphasize the right bits, and the rest can be kind of all blurry, and that's okay. Another big difference is turn-taking. Specifically here, the fact that the human is much faster to respond to the human than the system. That happened not all the time. It's not at every point that happened. Like in the before saying 51C, there was a significant delay here, and that's not a problem. However, in certain points, like after the user confirmed yes, the system was very fast. The operator was very fast to respond. Let me get that for you. And then it was a long delay to actually get the results. But this pace of conversation is very different between the two, and it's much more variable and flexible in the human case, and there are good reasons for that. And that's something our systems are not able to do yet. And finally, something that maybe is not as obvious, but there was some incremental processing going on in the human side here. You could hear as the caller was asking the question, you could hear the operator actually going through paper and starting to get the information about the 51Cs and then confirming actually that information later on. But that's something also systems usually don't do, starting to process things as the user is speaking to the system. And that's particularly relevant when you get systems that get more and more natural language input with longer input from the user. As long as you get yes, no answers or one-word answers, this is not really that relevant. But when you move towards more natural language, which is what current systems are doing, it makes more sense to start addressing issues like incremental processing. Now, these are many different problems and very hard to solve. So we're not going to be there tomorrow. Now, in the meantime, let's see what like a more reasonable, I'd say, short-term goal. So this is, I'm just like playing back the original.
What can I do for you?
When is the next 54C coming to 18th Street?
The 54C. Did I get that right?
Yes.
Okay. Where do you want to go?
Carson.
Going to Carson. Is this correct?
Yes.
Okay. Let me check that for you.
Now let's see. What I did then, I edited this audio to make it more like something like we would like to be, but still a system, but maybe the next generation or something.
What can I do for you?
When is the next 54C coming to 18th Street?
The 54C, right?
Yes.
Okay. Where do you want to go?
Carson.
Carson, correct?
Yes.
Okay. Let me check that for you.
Okay, so there are two modifications that happened here. Remember these four things I was looking at are actually, in this specific example, I addressed prompt design by shortening the prompts, which again is not the hardest thing to do in all these four. It's probably the easiest thing to do. And then I also shortened the latency in the right places. And this is, if we could get to systems that have this behavior, it would be a first step towards going towards completely human-like interaction. It's not there yet, but it's part, to achieve the whole human-like interaction, you need at least all four of these, and maybe more. And so, as a first step, I'm proposing, in this particular talk, I'm proposing to address the turn-taking problem. The prompt design, I'll leave that as a separate issue. Yes, Tim? I'm actually going to talk about that very specifically, but it's basically the fact that you don't know, you don't want to interrupt the user in the middle of their turn, and so you don't know if your user is going to pause in the middle of their turn or at the end of their turn, right? So that's using a fixed threshold for endpointing is what triggers longer latencies. It's not a matter of computation power. So, well, that's exactly what I'm going to talk about now. So what are the current approaches? What do systems generally do now in terms of turn taking? Typically, there's no explicit model of turn-taking in these systems. It's more addressed from an engineering point of view through an ad hoc combination of low-level tasks. I mean, it has to be dealt with, definitely, because otherwise you can't have a dialogue. It's usually just a combination of end-of-utterance detection, which is the minimum thing you need to be able to do to have a dialogue, and optionally barge-in detection and handling, if the system allows barge-in. But there's no general framework. And the problem with not having a general framework to model turn-taking is that first it makes it hard to optimize, and it's not clear what it means to optimize. And second, it's not well integrated in the overall dialogue model. And that's maybe more of a theoretical problem, but it prevents the system to learn, it prevents the lower levels like turn-taking to inform the higher levels like grounding and dialogue processing. And the opposite too. It separates the two so that turn-taking cannot be well informed by higher level information. I'll see how, I'm going to now propose two approaches to address these specific issues in this talk. So the bulk of the talk is about these two work that I've done during my thesis. First one is about optimizing endpointing thresholds, still within the very standard framework, but just changing how we set the thresholds. The second one is a new model for turn-taking itself, which is a more generic model that's going to encompass different turn-taking phenomena. And I'll give 2 examples of application of this model to specific problems like endpointing and interruption detection. So how is endpointing done in general today? It's usually a combination of 2 layers of processes. There's first the voice activity detector that's going to just discriminate between speech and silence in the incoming audio. Something like this. So let me explain this example first. You have the system says, what can I do for you? User responds, I'd like to go to the airport, with a pause after 2. And so your voice activity detector tells you that there's speech until after 2 when it detects there's silence. And typically the system uses a threshold here. If the silence here gets longer than 700 milliseconds, I'm going to endpoint. And in this case, because the user starts speaking again before the threshold, nothing happens and the utterance continues until the next silence is detected, same threshold is set, and this time the user doesn't start again, so it's endpointed. That's the very standard, very simple approach that's used in most systems. There are 2 different issues with endpointing in general, I would say. The first one is cut-ins, which is when the threshold is shorter than an internal silence, the system is going to interrupt the user in the middle of their utterance, which is in general not a desirable behavior. Or if you want to do that, you don't want it to be triggered by silences. You want the system to be aware that they're going to interrupt the user. And in general, that's not something you want. And the second problem is latency. That's exactly what I was talking about a minute ago. It's because you're using this fixed threshold, at the end of every turn, you're going to have at least the duration of the latency before you can respond. And in addition to that, depending on how the system works, you might have additional processing after the latency too. But at the very least, you would get the latency. And so you have a trade-off here. It's either you can set long thresholds, which will, I'm sorry, I don't know how to turn that off. Okay, which will trigger few cut-ins because you will have few pauses that are longer than that threshold, but they will trigger long latency at the end of every turn. Or you can set short thresholds, but then you'll have many cut-ins and short latencies. Yes?
So I would have thought that in that kind of case, you wouldn't see other things like phrase final lengthening and so on. That when I've got that kind of almost filled pause case, that I would have thought the end point of the first phrase would be really different from a case where I'm saying over your turn to talk. And it isn't just the silence.
I totally agree with you. That's a very good point. It's exactly what I will discuss in just the next few slides. The thing is, most current systems basically ignore all that information because all the input they have is voice activity.
Is considered a distortion of kind of one thing that you have to correct for, not something you can actually use as a signal.
Right. Basically, yeah, that's true. I mean, it's definitely prosody. I mean, there are many different features. I'll just explain those in a minute. So there is information. It's just not used. Sorry. Let me just try and turn off. Hopefully that's going to help. Right. So what we would want, because we have this trade-off, is something that tells us that we should set different thresholds for different silences, right? We want to set a long threshold when it's an internal silence to be sure we don't produce cut-ins, and we want to set a short threshold at the end of the utterance using all these kind of information we can get. So specifically, what kind of information do we have in a spoken dialog system at our disposal for this to inform the threshold setting? First, you have discourse. You know which dialog state you're in. Like in the example I will use, which are all based on the Let's Go bus information system, I have a very simple abstraction of dialog state. It's 3 different states. Is it an open question, like what can I do for you? Is it a closed question, like where do you want to go? Or is it a confirmation question, like more yes, no type of question? But that kind of information helps you set the threshold. Another very important source of information is semantics. In particular here, I'm talking about using the partial recognition hypothesis that you get at the beginning of the silence. When you detect your silence, you know your recognizer can tell you so far what it has recognized, and you can use that to inform your again, threshold setting, because that's going to tell you if the user is likely to be done or not. You can use prosody, exactly like we were just saying, which includes intonation, duration, vowel lengthening, etc. All these that are very well known in human-human dialogue to actually affect the perception of turn taking. You can use timing. Very simple features like how long ago did this utterance start is likely to be some source of information on whether it's going to finish soon or not. And we can also use information about the particular speaker we're dealing with. And that can be either you have access to many different sessions with the same speaker. In my case, this wasn't the case. So I'm using information from this particular dialogue. But you can use information from the first few turns to inform your behavior in the later turns of the dialogue. Information like how many pauses does this particular user make, how long are they, etc. And so we have all this large set of features that we could use to set the threshold. What I did, I'm not going to describe my algorithm here, but I designed an algorithm that specifically builds a decision tree based on these features by asking binary questions on these features. And at the leaves of the decision tree are thresholds. So it's a fairly simple, in just 2 words, it first clusters the pauses that are in a training set. So of course it's based on a training set of collected dialogues where each pause is annotated as internal or final. And this is done, this annotation is done automatically. So it's completely unsupervised in that way. So it's going to cluster the pauses based on the features, and in a second step, it's going to set the optimal threshold in each cluster. And that's how you build a decision tree this way. This is published in my SIGDIAL paper this year. So there's no point in going through the tree in detail, but what I want to show here is that it does make use of many different features. So the different colors represent different feature sets. You can see things about, like the first one is timing here, pause start time. The green ones are all about semantics using partial recognition hypothesis. The orange one is about dialogue state. And the other red one here, red ones, are about the behavior of the user in this particular dialogue. Yes?
Are you going to tell us how you unsupervised learn the structure?
It wasn't included in this particular, because of time constraints, I didn't include it here. I can deal with that maybe after the talk in the questions.
So the key point is unsupervised.
It is unsupervised, yes, yes.
Can I just ask one question on that? So how do you get the training data? Is it a system that just waits?
Okay, right. A very good point. This, in this case, it was a system that used a fixed threshold, 700 milliseconds, so reasonable, not very, very long. And so that introduces, that's where the unsupervised learning is risky, because your system at runtime is going to make errors, right? And so what I used is a heuristic that after the fact can tell me whether a decision was right or wrong, and a particular endpointing decision. And there are hints on, I mean, it's not a perfect algorithm, but there are hints that tell you if the user starts speaking again right after you endpointed, it's probably that they weren't done speaking because they're not responding to anything, the system hasn't spoken yet. But if you hear them speaking right after your endpoint, that probably meant that that decision was wrong. I'm using this kind of heuristics to relabel or to correct the annotation, the annotation of the training set. And then based on that, I retrained the...
Errors already in the log.
Well, you can know it's an error for one, and you can have some hints because if the user did start speaking again, you can use that start time to measure a pause duration. Even if you had made the decision to endpoint, if the system at runtime made the decision, you still have the last time the user spoke and the next time the user speaks, and you can use that as a pause duration that's longer than the threshold used at runtime.
So is your question that you are asking is, you come up with this new system, and the question you are asking is, had I deployed this new system, how well this new system would have been better than your one? Is that
right? Well, I'm going to explain I have 2 different evaluations. I'm going to explain that in the next slide. Yes.
I'm wondering why supervised methods are off the table. So I'm thinking, if I have a large amount of recorded dialogue from, say, 2 speakers that are easy to separate, say a man and a woman, and then I could tell after the fact who was speaking when, and I can look at all the pauses in that arbitrary amount of speech, and at any point in there during a pause, I could say, "Can you guess whether the speaker A or speaker B is going to speak next?" And I would think you could get arbitrary amounts of data of this kind.
Oh, you mean by detecting the switch between the speakers?
Can do speaker identification or separation,
right?
And if I pick dialogues for which the separation is easy,
right? That is true. The thing is that requires human. That would be based on a human dialogue,
right?
And so then that's true, but then there are differences.
Model, I think I could do a very good job of this,
right?
Predicting which of the 2 speakers is going to speak next.
Right, I see the point. The approach I was taking was basically starting from a system and kind of improve this particular system over time. So I was trying to learn directly on the system. And so in terms of evaluation, how did that perform? So this is performance in the by cross-validation in the actual training set that I collected, corrected in the way I just explained. The dotted line here is the baseline using a fixed threshold. And so what this represents is it's a kind of ROC curve, if you want. It's the trade-off between your latency and the cut-in rate. So of course, if you have high latencies, you're going to get small cut-in rates. And if you have low latencies, you're going to have high cut-in rates. And you'll have to trust me on that. But reasonable cut-in rates for a workable system tend to be in the range of between 2 and 5%, I would say. And that corresponds to like fairly standard, if you look at the baseline, fairly standard thresholds that are used, which are usually between 500 and 1 second. So, yeah. And so what this does, what you can see from this graph, so the different lines represent using different subsets of the features to perform the training. And the blue line at the bottom is using all the features that I described before, the feature sets that I described before. So first thing is that, well, to some extent it works because we did get a significant improvement, about 22% reduction of latency at a certain cut-in rate if you take 4% here. Or you can look at it the other way and say if you can keep the latency constant and reduce your cut-in rate by 38%. The other thing that this shows, which when you look at the different feature set, is that semantics is by far the most useful feature type. It's not that the other ones don't work at all. I mean, they all bring about half of the overall, except for semantics. But once you add semantics into the mix, like the partial recognition results, it's also given the structure of this particular dialog that's fairly constrained, etc., of course. But given all that, semantics are really bringing you most of the gain here.
What do you mean by discourse?
The discourse is mostly dialog state level features, and yeah.
So it's not part of the semantics, and semantics is just per semantics?
Yeah, I mean, there's kind of a blurry. I'm not making strong statements about the name of these sets because semantics also contains the understanding of the particular partial recognition hypothesis given the current state. It's semantics within the current state. So if you ask a yes/no question and you get a yes, this is a high semantic score. If you ask a yes/no question and get a time, then it's a low semantic score.
Discourse.
It has some context to be fully honest. Yes.
Just to get just to clarify, with respect to the decision tree that you had,
yeah.
That decision tree is giving you a threshold on how long to wait
in a pause.
In a pause, right? And with respect to the cut-in rate, a cut-in can be, what I'm trying to figure out is whether it's that bad to cut in. Like sometimes, I mean, like if for instance you have some semantic information, like some slide information, and the user's still kind of trying to figure out, well, where am I going to? It's okay to cut in and say, okay, I heard that you want to go from here to whatever. Now, where do you want to go?
Yes, so, I see your point. That's true that cut-ins might have different costs in different circumstances. It's not, I totally agree, it's different. It's hard to actually get a hold of this cost. I mean, definitely if you have some information already, that helps. That might still be very confusing for the user because if the user starts speaking again and then that barges in on the system and then you can get in actual turn-taking conflicts in a system and that can be very confusing to the user. So
what is it currently doing right now when it cuts in? Is it just implicitly confirming anything that it knows, or
it's trying to explicitly confirm what it knows, or if there's nothing, it's sending a non-understanding prompt, a repair prompt. Yes.
I'm wondering what are these durations in natural terms, among humans?
So
I would have thought a second is just eternity.
It actually depends a lot. I did, unfortunately, I don't have that right here, but I did a study on the corpus of human dialogues, like the example I played from that corpus. And what happens is that you have a really wide variability in the human. Some cases are actually 1 second or more, and they are not necessarily strange or uncomfortable. But some cases are really, really, really short, and they have to be. So it really depends a lot on the context, on the type of dialogue act you're having. So it's hard to give.
Under 100 milliseconds.
Oh yeah, it's 0. You can have overlap too, actually. So It's virtually zero.
Like Tim is saying, in fact, in our conversations,
Right.
at least depending on different ethnic groups, it's not a route to logic.
Right, but the fact that it's zero doesn't mean that you're cutting in on the user. You might just be very, very confident that they're finished saying whatever they're saying. And you're just very, very close to their turn, but you don't really interrupt them in the sense that they weren't intending to say more after it.
So it turns out that social linguists and psychologists like looked at different pauses and pause lengths and found that in certain disfluencies, like you were mentioning before with respect to pauses, if someone says an then the pause is much longer than if they say an and users don't interrupt because they understand that meaning that they're thinking.
That's probably what phrase final length is all about. It's over, it's your new choice. And you probably don't even have to wait for the final.
Right.
So yeah, I mean, the human case is actually much more complex in general. But also, I think, well, complexity, I mean, is maybe arguable, but definitely...
If we looked at the short end of this, I'll bet 300 milliseconds is great because of not start. It's just too long.
In terms, well, it depends. I mean, in terms of being human-like, yes, I agree with you. In the cases where it's slow and it's okay to be slow are fine. But in terms of short end, yes, I agree. We're not there yet, definitely. Even with the improved one, it's going there, but it's not there yet.
But is it your goal to fully reproduce a human-human conversation experience?
Well, it's one goal you can think of. The other one is to relate this matrix to user feedback about the interaction they have with the system. So basically to user satisfaction. Right. Unfortunately, I don't have that here. It's a very hard thing to get because it's hard to get feedback on these kind of subtle things directly from the user. And in my particular case, I'm using a system that's used by the general public, and we don't have access to the users after they've used the system.
There's nothing wrong to let user know that they are interacting with a machine, right?
Yes, but on the other hand, something I forgot to mention, when like the two machine examples I played at the very beginning, it's not only about interaction, but if you just look at dialogue duration, these two, when it gets to very short dialogues like these ones, the difference between the two was like 25%, just by shortening the prompts and the latencies. And so that can also mean something just, economically speaking, if you have a system deployed out there and you want short dialogues. So gaining here and there can actually add up in the end. But I think it's mostly in how the interaction flows.
The only problem I have with this is actually, the end sentence timeout, that concept was a very low concept, buried down in the SR engine. Right, so something like SR engine has to make decisions without knowing those what the application is going to use that information, right?
Well,
so do you happen to have a hard time to implement this in your system?
Right. So actually, it's a good plugin here because I did implement it on that system that I played, that I showed, because I'm not discussing the whole architecture here, but it's a research dialog system, so it has a fairly complex architecture, and particularly I designed it so that it has a central component that's in charge of low-level interaction. So what the ASR does, it just feeds information about voice activity detection, partial hypothesis, etc. But the decision to endpoint is actually made by an external module that also has access to high-level information, etc. And that might add a little bit of delay, actually, but it's very small compared to all the other factors here. And that makes it more computationally expensive than a standard, like commercial dialog system. That's from the research perspective. So I did implement the specific tree that you've seen. The example I showed I implemented it in the Let's Go interaction manager, which is this central component. What you might have noticed in that tree that there was no prosody, because for the live version, because prosodic features are very expensive to compute and not as readily accessible as the others, and didn't bring anything in terms of the batch evaluation, I didn't include them in the live version. I picked a working point because now I have these curves. Now to run the system, I have to decide where I run on the curve. And I picked the curve. I picked the one at 3% cut-in, which was 635 millisecond average in the batch evaluation. And I ran a study in May 2008 where I just set the public system to use randomly one of two versions, either a fixed threshold of 700 millisecond or the decision tree. And now let's look at results out of this. So first, the average latency. Here, the left side is the average latency overall, and this is split by dialog state. Note that this time this is real latency. It's not threshold value. This is the actual time between the end of the user utterance and the beginning of the system utterance. So it includes additional processing, which is why it's higher than previous values. Well, first kind of disappointment here is that there's no difference at this point. We'll see why in the next slide. It's not a bad thing. But even then, the behavior induced by the proposed algorithm is very different from the control one. The control one, of course, uses a fixed threshold. There is very little difference in terms of latency between different states. It's mostly random difference. However, in the proposed case, basically the algorithm learned that after an open question, which is typically where you get users to say long utterances with pauses, hesitations, etc., it learns to set longer thresholds, which end up being longer than the baseline. For closed question, it has an average behavior similar, same as the baseline. For yes/no question, which are much more predictable and where there are like definitely fewer pauses because the user mostly responds yes or no, not only but mostly, the system learns to shorten the latency. It's still not short enough, I would say, but it's definitely significantly shortening the latency. Sorry, that's what I just said. Now, if we look at the cut-in rate, this is what explains why we had similar latency. We were actually working kind of along a horizontal line here. We significantly reduced the cut-in rate here overall, and this came mostly from the open request state, which is for the same reason as before. The system learned to set longer thresholds there because that's where most of the cut-ins happen. You can see in the control case, 12% of the turns are cut in that state. That's definitely a significant number of them. Even if they're not very costly cut-ins, some of them are definitely bound to be problematic. Yes?
Your results make me wonder what would have happened if you had as a baseline policy, just don't cut in unless you have any kind of semantic information, which would reduce the open questions. So in other words, just cut in only when you have some slot information, like,
and a fixed threshold.
Not necessarily a fixed threshold, just whenever, maybe you have to have some thresholds, but, having just without using a sophisticated decision tree, just basically only cutting in after a threshold when you have some information. Right?
So
otherwise, you just let the user continue.
Right. The thing is, like specifically in these turns, it's likely that the user would say more than one piece of information. So you would still end up cutting in. Now, if you decide that these cut-ins don't matter, they might be okay, but there's still uncertainty there. So in terms of raw number of cut-ins, there would still be some. I don't have the numbers, so I can't completely answer. But I think there would still be some because of that. Because people would start saying something, and it would not be done, but there would still already be some semantics. But the other thing you could imagine doing is to set a state-specific fixed threshold, right? You could just learn. But the interesting thing here was to learn that from the features. We couldn't know for sure beforehand which one would be more useful or less useful. I mean, we could have guessed definitely some intuitions, but this actually learned it from data and then did optimize it.
That's actually something I wanted to ask you. So, I've actually worked on designing IDR systems. So best practices there is, you know that yes/no confirmations are very special, and you tune that separately. And so first question is, how much of this improvement comes from tuning just the confirmations? And the second question is, the other baseline would be, like we said, just a static, just set per dialog state.
Right.
How much are you improving from that baseline?
Right. So I don't have the numbers. I did compute them, but unfortunately I forgot the numbers for the state-specific threshold. It was not exactly. It was kind of halfway between. It was going there, but not completely. Not as good as the proposed approach. In terms of confirmation, I do agree that because Let's Go has a lot of explicit confirmation, that's a big factor in the improvement. It's not all, because like this improvement here is something that's not related to confirmation, but the gain in latency, a lot of it comes from the confirmation questions, like we've seen in the previous slide. Now, the interesting thing about this is that because it's a learning algorithm, then if you have more complex systems like different states and different things, you can still rerun this. And since additionally it's unsupervised it's unsupervised, you can always rerun it if you add a different state to your dialog that's not non-standard. You can learn from interaction with the user. Now, the last thing I wanted to see on this live evaluation, which I couldn't see in the batch one at all, was the impact of the algorithm on more speech recognition performance, if you want. Now, the problem here is this data is not transcribed, so I don't have word error rate value directly. So I looked at the non-understanding rate, the number of rejects, the proportion of rejects in the user speech, proportion of utterances that have been rejected between the two conditions, and there were a statistically significant reduction both overall and in yes/no questions. And so overall, it's like 1%, so it's a small reduction, but it's statistically significant. The biggest surprise to me was that the improvement was here in the yes/no questions, because the reduction in cadence happened in the open question case here. Now, the reason why this happens is because the recognizer, when you have a very short word and you add a long silence to it, you're more likely to mess up your recognition, basically. That the impact of the silence, if you have background noise and background voices, is going to hurt recognition even of the actual word itself more. So that's the explanation I have for this reduction here.
So did you see an overall significant difference in task completion?
No. It wasn't sensitive, like these metrics are not sensitive enough for that kind of improvement.
In that case, just to clarify, you're saying that in this system, when I'm trying to get the answer to a question, yes, no, it's a binary question, yes or no, that we're only getting, 5 to 10%, or 95 to 90% right.
No, that's not exactly
or
what that...
at least that we understand that we got it
Right. The thing is that some of these are not even speech in the first place. Right.
So we asked a question and the user didn't answer it.
Right. There was some background noise, some baby crying on their lap, or some. We have lots of data like that in our corpus, unfortunately.
Right. But is it actually 7%? What's the fraction if you ask a yes/no question that you actually get either yes or no as the answer?
I don't have that. It's maybe, I would say it's 80%. Or
really? So you're saying 20% of the time you don't. There's a third choice that they didn't.
Either they say something else, or
no, that I understand. They would say something else, but it would be something else that would be interpreted as either yes or no.
Oh, that's not what I said, and I don't have that specific number. Like in this case, I'm not saying it was interpreted as yes or no. It was just something that happened after a yes/no question.
Right. And you're saying if a baby cries, you'll get the wrong answer?
No, you'll get something that might be misrecognized as speech, but in this case, it would lead to a non-understanding. Say, I didn't get that. The system would respond, I didn't get that, which is not as bad as misinterpreting that as a yes, for example.
But still 10% is pretty much, even 5.
This is tough data.
When you say speech, do you include like spontaneous speech, like the kind of thing means yes, no, right?
Yeah, well, what I mean here is the question the system asked. What comes from the user can be...
It can be speech like...
Right.
It's not speeches. It's not languages, though.
Not necessarily, right. Yes.
Here.
Yes, because here I don't have any label of what the user actually said. I don't know what the user actually said. So they are included, yes. Yes?
So one thing that you could do to see if users can perceive, you were saying before that, after the users use the system that you couldn't really ask them, questions. But you could certainly just take the recorded audio and present them to a bunch of raters and have them rated along certain dimensions and see if people can distinguish between, the small, subtle changes that you made. And I'm wondering, have you done that? And if so, what were the results?
Right, so I'm starting to look into that. My take on the preliminary result was that I think we need more improvement than this. I didn't do a formal evaluation like this, but from what I looked, is to make it really sensitive. I can hear the difference, but to make it very sensitive or perceptible to the listeners, to third-party listeners, I think we need to go further than this. Even in the best cases, even in cases where we reduce. There are lots of yes/no cases where we reduce latency by 50%, say from 1 second to 500 milliseconds, and that's very hard to perceive. It's surprisingly hard to perceive, actually. So I think we're not completely there yet, is the answer. But I don't have this formal evaluation. I started looking into it, but I'm actually trying to improve more before doing that evaluation because it's more costly than batch. Okay, so that's it for the first part of my talk. So it was still a principled approach in the sense that I was optimizing from data the turn-taking behavior or the end-pointing behavior, but it was very much in the standard framework of setting a threshold and just making a decision, the end-pointing decision based on a threshold. Now, what I want to take one step further and propose a new way of addressing turn-taking in general. It's more of a theoretical model that will be applied to specific problems, and I will explain that. So if we want to describe what turn-taking is in the kinds of dialogue I'm looking at, which are two-party dialogue between the system and the user, at the most fundamental level, the floor or the turn is basically alternating between system and user in a loop like this, right? Now, the interesting bit is not that phenomenon, which is well known and not very special. The interesting thing to look at is what happened at the transitions. This is what we want, because this is where we can improve behavior. So one typical standard behavior is, say the system speaks, they finish their utterance, they free the floor, so they stop speaking, the floor is free, and it's marked to being for the user, but still the user hasn't spoken spoken yet here. And then the user starts speaking, gets the floor, finish their utterance, the floor becomes free but marked for the system, and we have this loop, and they take turn with slight pauses maybe between each turn. That's not the only way transitions happen. The other way is when they actually overlap. And so in this case, the system speaks, and before the system finishes, the user starts speaking, so it's marked, it goes to this state, it's marked as both speaking or both claiming the floor, with marked because the user is trying to claim the floor now. And if the system stops speaking, then we're going to switch to user. So you have this kind of transition. I'm going to, in the next few slides, explain how this fairly simple machine, which actually has a few more details. So first, each state you can stay in each state indefinitely. Well, yeah. And also the difference, I don't know if you saw the difference, but there are added arrows that you can actually go back, even if for example, the system speaks, user starts speaking on top of them, but then the user stops speaking, you go back to system. So you can actually go both ways in certain transitions. So this is still a fairly simple state machine, but it captures really many of the typical turn-taking phenomena that we observe in a two-party conversation. So first, smooth transition is basically the one I explained first. In this case, from user to system, user speaks, user yields the floor, floor becomes free, system grabs the floor, we have a smooth transition. Now, if after the user yielded the floor, the system waits, then we have a latency. That corresponds to exactly the latency that I was talking about in the first part. Okay, the staying in this state here. Now, if the system grabs, the floor is still to the user and not free, then we have a cut-in. Same thing we were talking about. Now, for a completely different kind of behavior, say the system speaks, finishes speaking, so we switch to the free U, but user doesn't get back to the system, so at some point system decides to grab the floor back. That's typically a timeout type of behavior. Didn't get response from the user, decide to grab the floor again. Another phenomenon that's very common, barge-in, user barge-in. So the system is speaking, user grabs the floor, so they're both claiming the floor at the same time, and the system yields, so we go to the user, and it was a smooth barge-in transition. And there are many other types, but the point is that this fairly simple architecture captures really a lot of the phenomena that happened and kind of formalizes them in a nice way. And so based on this, we can construct build an algorithm to make the decisions. And it's based on decision theory. I call it a dynamic decision process. The idea here is that at every point in time, system has partial knowledge of state, meaning that at some point the system is going to be pretty certain who has the floor. Like in the middle of utterances by the system or the user, it's usually pretty clear that the floor is user or system. But around transitions, there are points where suddenly you're not sure anymore who has the floor, and that's the point where you have to make the decision. So it's important. So you need to keep track of this uncertainty if you want to use that to take make your turn-taking decisions. There are the type of actions that can be taken either by the system or the user, but in terms of we take the viewpoint of the system here, is grabbing the floor, yielding the floor, keeping the floor when you have it, or waiting, which is not doing anything when the other person has the floor. And these different actions yield different costs in the different states we have there. They are not possible, not all of them are possible in all states, because for grab and keep, the system needs to have the floor in the first place, versus for yield and wait, needs to not have the floor in the first place. but most importantly, they have different costs, and we'll see what that means. And so once you have that, you have states in the world with a belief on what the current state is, and you have actions with costs. This is very decision theory oriented, and so you can use decision theory to pick the action with the lowest expected cost, right, using all this information. So now let me explain how, like using two examples, how this can be applied. So endpointing, again, typically you know that the user has the floor. You're at a point where you're pretty confident the floor is to the user. They've been speaking. And at some point, because there's a pause in the user speech, you're uncertain on whether the user just freed the floor to this state or the user still has the floor because they intend to continue speaking. And the user, in either of these states, the system can take two actions, grab or wait. If you're in this state, grab is the right thing to do because the user is done speaking and you don't want to induce latency, which is what wait does. If you're in this state, wait is the right thing to do because the user is not done yet, so you want to wait. If you grab, you're going to induce a cut-in. And so you can translate that into an actual cost function or cost matrix here. Again, this is once a silence has been detected in user speech. We'll see how that is important later. So the possible actions are wait and grab. The states are user or free S. And for the right actions, I set a cost of 0, the right thing to do, set a cost of 0. And for the other ones, I set different costs. For waiting, the cost is equal to the time since the silence has been detected. So the longer you wait, the longer the cost of waiting more is going to be, the higher it's going to be. For cut-ins, I set the cost of a cut-in to be a constant all over the system and all the states, which is both of them are kind of approximations, right? You can imagine cut-ins have different costs in different circumstances, and you can imagine this dependency not being strictly linear, but this is the first approximation to show how this system can be used. So now we have again a typical decision theory problem where we just want to take the action that minimizes the expected cost, given that the user is still silent at times t. Because if the user starts speaking again, then we're going back to being certain to being the user state, and so we don't have this problem anymore. So we assume that the pause is still going on at time t, and the cost of grabbing is the probability of being in the user state times the cut-in cost, plus the probability of being in the free state times the cost, which is 0, and same thing here for wait. So we have these two expressions that express the expected cost. Now, what we need here is to compute these state probabilities. We need to know the probability that the state is user or free at times t. Now here I'm using the actual expression is with conditional probabilities, but because they're both conditioning on the same thing, you can use joint probabilities. It's equivalent in terms of solving the equation in the end, of finding the point. So I'm actually expressing now joint probabilities. You can use this with the definition of conditional probabilities here. The probability of being free times the probability of being in a pause given that the floor is free. Now I make this approximation that if the user released the floor, they're not going to start speaking again, ever. So it's an approximation in the sense that we're going to get these transitions back to the user state if the system never gets back to the user. But these usually happen after a fairly long time, which is not the same scale as what we're dealing with. So for now, I'm saying that if the user did free the floor, they're never going to start speaking, so they're going to be silent regardless of t. So this probably is 1. And the other thing here is that because this doesn't depend on whether the silence is still going on or not, I've removed that conditioning, then it doesn't depend on t anymore. So it's the same as the probability at the very beginning of the pause that the floor was free, that the user had finished their utterance, basically. So we have this. Now we'll need to compute this parameter. But this is no longer dependent on time. Sorry, that's what I said. Now, on this side, like the other probability of being in the user state, same decomposition here. The only thing here is now the probability of being in the pause at time t, given that the user keeps the floor, is the probability that they haven't spoken again yet. And so it's the probability that the duration of this current silence is bigger than t. And we can use that if we compute the probability distribution of internal silences based on data. And that distribution is well approximated by an exponential distribution, which is something other people have found in the literature in the past, and I've confirmed that that's a fairly good match on my data. And so I'm using this approximation, which leads to this probability to be just equal to exponential minus t over mu. Mu is a parameter which is equal to the mean pause duration. It's something you can compute easily. And on the other hand, you have the same phenomenon as before, because it's no longer dependent on whether it's a silence. It's equal to the probability at time 0 that the user kept the floor, or keeps the floor now. And this is 1 minus the probability we had in the previous state. So we just have two parameters to compute. Mu is just the mean pause duration. Now we still need to compute this probability. So at the beginning of the pause, did the user yield the floor, or are they keeping the floor, is the question. So this is a very very standard binary classification problem. You can take all your pauses in your training data and label them as internal or final, and use the features in the same way that I was doing in the previous algorithm, use the features that are available at the beginning of the pause to try to predict this outcome, whether it's final or internal. And I did that using logistic regression. And here are the results. So in terms of raw classification error, the majority baseline is 24.9% and went down to 21.1%. So of course that might seem like it's not a very high, a very large improvement here, but that should not come as a surprise, because if we could do a very good job here, we wouldn't have to wait for any threshold. If we could know at the very beginning of the pause whether the user is done or not, we wouldn't have to wait at all, ever. And it's not only a matter of having the right features and the right algorithm, there is some intrinsic ambiguity here. There are points in time where the user might be done or not, and you're not sure, you're just not sure about it. Even a human is not sure about it. Even the speaker might not be sure about it, actually. So it's not a surprise that you can get a very, very high accuracy here. You could probably get better with more features or with different classifiers, maybe, but I don't think it would get much better. But that doesn't matter, because what we want is an estimate of the probability. We don't need to have perfect classification. And because we did get improvement in both hard and soft metric, like log likelihood, this at least improved over a simple prior distribution. So we can use that and plug that in our equations. So what happens here is you remember we had these two costs, the cost of grabbing, the cost of waiting, and they work this way. So the cost of waiting was directly proportional to t. It was t times k, so it's just a linear increasing here. The cost of grabbing, the cost knowing the state was fixed, but because our knowledge, our belief probability on the state decreases exponentially, so we have this decreasing cost and this increasing cost, and basically you want to endpoint when the cost of waiting gets higher than the cost of grabbing, and so the intersection is where you want to set your threshold, because we're in a pause, we can actually go back to setting a threshold here, which is the time that corresponds to the intersection. So in other words, the threshold is the solution to this equation. Now this doesn't have, unfortunately, an analytical solution, but you can find numerical methods and solve that very easily, even at runtime. Now these are the results using this approach. Again, this is the baseline with a fixed threshold, and this is the dynamic decision process approach. It's slightly better. I don't have it on this graph, but it's slightly better than the previous approach. I don't have it here because this was done on different data, but I also have it. I did the same computation on the same data as before, and it was very slightly better. Now the interesting thing is we're not done yet. So it wasn't, the goal was not, the hope was not that this would be significantly better than the previous approach. The interesting thing here is that we can extend this approach much more than we could the previous one. Because we have this generic framework, we can apply this at different places, at different ways. So an example of an extension here is to not only do endpointing at pauses, but also in speech. You can have a similar process within utterances before you detect a pause. And that's important because pause detection itself incurs a delay. To be sure you have a pause, you first need to wait something like 200 milliseconds for your voice activity detection to know. Also because there are silences within speech at consonants like P's and T's that would have potentially long silences within them, not being a pause at all.
I mean, the silence of the stop isn't anywhere near 2 minutes.
It depends on the language, not in English, but in some. But no, I agree. But
But how fast can you compute this dynamic decision process?
So well.
Make this worthwhile.
I don't think the computation of the threshold is going to be high. So what's before the threshold itself, there's the feature computation, which also happens like during these 200 milliseconds that I'm saying. It's both to detect the pause for sure and compute the features. So you have this thing that kind of introduces a delay right off the bat here before you can make any decision. So if we can start detecting the floor switches before we detect the pauses, at least for the cases where we're pretty sure that the user is done, then that would improve over the current state. So what we can do is use partial recognition hypothesis directly, even without pause detection. And in this case, I define the floor switch because we don't have a pause to classify binarily between internal and final. But I say that the floor switch is at the first partial hypothesis where the text of the hypothesis is identical to the text of the final hypothesis in the training data. Because in the training data, the system actually went on and did standard endpointing at the end. And if the recognition results are the same, that means we didn't gain anything by waiting some more, so we should have endpointed earlier on. So this is how I label the training data here. And now we can use, again, the similar cost matrix. We're in the same states and same transitions, same actions. Again, the right action has cost 0. Now, the cost of a cut-in is still the same constant k, and the cost of not endpointing when we could have during speech, I set it to be a constant d, so another constant. Because we don't have this dependency on time anymore. We don't have this thing where we wait once the pause starts, we have a certain duration. It's something that happens at every time we get a partial hypothesis. So this one is no longer dependent on time. So what that means is that these equations basically lead to a threshold on the probability, at this particular partial hypothesis, the probability that the floor is switched or not. So we can do the same thing as before, use logistic regression, but this time we classify not pauses, but we classify partial hypotheses as being final or not, identical to the final or not. So we have a classification, the baseline is higher, and we get to the relative improvement is much bigger than the previous one. We're still at 20%, basically the same value, 20% error. But again, we want to use the probability estimates rather than the pure classification. So that's not necessarily too bad. So what happens here in terms of results, is we do get some improvements. They are small, I would say. Over the endpointing at silences only. Now, what's interesting to do here, the problem is that this latency metric, average overall latency metric, is not necessarily exactly capturing the user experience very well. So it's kind of interesting to look at the distribution of the thresholds picked by the two approaches. So this is the different values for the threshold. This is the proportion of turns that have this threshold given the algorithm. And this is, the blue one is endpointing at silences, the first approach. The second one is endpointing anytime including potentially during speech. So what happens, first you look at the end of it, they are completely overlapping, so there's nothing that changes in terms of long thresholds. What happens is, of course, at 0, which is during an utterance, the original approach didn't have any didn't allow this, so it has 0% of the utterances here. The new one has 10%, so we still have 10% of the turns where we're going to have much faster response than we had before. And basically, some of the high, like the original blue distribution has 2 peaks, one short and one long, kind of. And what happens is some of this peak has been transferred to 0 latency. So these cases where we're pretty sure that the user is done, turns out some of them we can actually decide before we detect the pause, and some of them we can't. But it still leads to 10% of the turns where we will reduce the latency significantly. And it's not, I'm currently working on doing the live evaluation for this, because it's not clear that just putting a 0 latency translates exactly what's happening in the real live system. Yes?
You use the model to try and predict to make decisions about whether you grab or wait with human calls. So you have human calls, and you're just you treat this as an interaction with an automated system. How well would that match what human beings have?
Right. So that's a good question. The problem with that is getting the features in human calls. One thing, like semantic features, etc. One thing with, I mean, it's possible. It would require heavy annotation, basically, of
But isn't it using? It's the same task, right?
Right, but I'm not doing any human annotation at all so far. I'm purely relying on automatic features.
Okay.
So
yeah, it would require
so yeah,
annotation.
Right. So it is an interesting point. I don't have the data labeled for that. And the other thing with that kind of evaluation, it's interesting to see. Now, if you don't match exactly the observed behavior, it doesn't necessarily mean you're completely wrong either, because there are different acceptable behaviors. So, but it's definitely more information.
Did you say that when the system actually barges in, did you measure that as 0 for the red curve?
Well, I wouldn't call that barging, but yeah, for the red curve, yes.
The system starts speaking before the user.
I count that as a zero threshold.
0. And so why is there not a discontinuity at 0 then? So you get...
Yeah, well, these curves are smooth, actually. So there is a discontinuity. That's a good point, yeah. So there's 0, and the first available point after that is 150 milliseconds, because in this case, the minimum threshold was 150. But the points are actually every 150 milliseconds in this case. But you can't get anything between the two. That's a good point. Okay, so that was, well, I've talked enough about endpointing for today, I think. So now I'm going to show how this can be applied to different problems. This is not completed yet, something I'm working on right now, so I don't have final results. But it's interesting because it shows how the model can be applied to different problems and the same starting model. So barging detection, this time we're in the case where the system has the floor, and now we come to this point of uncertainty where the user might be trying to barge in. So our voice activity detector tells us there's speech detected, for example. And so we might be here, but it might be some noise, and it might be the user just back-channeling on the system, not trying to grab the floor, but just providing some simple feedback without trying to interrupt the system. And so the kind of actions, there are two actions that can be taken again, but this time it's keep the floor or yield the floor. And if you're in the system state, you want to keep. If you're in the both state, when the user actually did start claiming the floor, you want to yield. And so you have a very similar structure as before, actually, cost structure as before, with different constants. But you can have the same thing, that the cost of staying in the both state is going to be equal to the duration that we've been in that state. So the longer you stay, the higher it's going to cost. And the cost of yielding when you shouldn't, meaning that the system interrupts itself, although the user wasn't even speaking or wasn't trying to interrupt, is a constant, is set as a constant. And the interesting point here, the difference with before, I mean, the rest would be very similar equations, obviously. The difference with before is we can use prior information here. In addition to the standard logistic regression approach or any other probability estimation approach that I described, you can introduce priors, which we didn't have before. In this case, you can look at previous data, a corpus of recorded data, where you have the prompts, system prompts, and you can measure when did users barge in. You can compute the distribution of the times where users barge in for specific prompts. Because barging is going to be triggered by certain things in the prompt, the content or the prosody, and so you can look at that actual data and use that as prior information on, at this particular time, the user is likely to actually barge in. Because random noises are not going to follow a specific distribution. They're going to come randomly with a flat distribution. So this can account both for discriminating between real speech and noises, as I just said, but it can also account for discriminating back channel versus barging, because it's likely that certain point in the prompt are more likely to trigger back channel from the user. Others might be more likely to trigger barging. And I did compute this on the Let's Go data on an older set of dialogues, 6,000 dialogues, about 127,000 prompts total. And this is an example from one prompt. The system is saying going to, this was normalized because of course this varies every time, but I normalized the varying part to give it the mean duration. Is this correct? So going to the airport, is this correct? And you can see how barging happens here. It happens first very, very much at the beginning of the utterance, which means the user barging in here are not responding to this utterance. They are responding to something that happened before, and they're speaking. It might be actually a cut-in, where the user was not finished speaking, and the system started to respond, but the user continued their utterance, and so it resulted in a very early barging. So that's one type of barging we get, and which we might want to consider not as a barging, actually. That's an interesting choice to make here. Another one here is after going to the airport, people typically backchannel, give the response yes or no, or particularly when it's yes, they will just give you one single answer here. And in this case, because we're doing explicit confirmation all the time, it's okay if that's taken as a barge in, because anyway we were going to ask this question. But we can use this information to structure, to help implicit confirmation as well. You can imagine an implicit confirmation that would be exactly like this, except saying, going to the airport, where are you leaving from? You can change the second part. Because of the way the prompt is worded, you can just change the second half and have something that's an implicit confirmation rather than explicit. And then you can use this, that if you get a barge in here, you know that this is not going to be, you know, you should continue speaking the remaining of the prompt. Because the user is, particularly if it's a yes, the user is just providing an answer to a back channel to this part, and they still want to hear the rest of the question. So you can use this to inform, although the data contains explicit confirmation, you can use that to inform the design for and the models for implicit confirmation. And the fact that we get all these barge-ins and different user reaction with implicit confirmation is one big reason why it's so hard to actually implement implicit confirmation in really deployed system, because the behavior is so much harder to predict. And you get, you know, in this case, you would say going to the airport, where do you want, where are you leaving from? And you get the user saying yes, and then you interrupt this prompt because you heard yes, and so you don't want to do all this. And so this is something that could help, and could be used, plugged in very easily in the framework I proposed, because it's just a prior probability on the state, given the time at which it happens. And so there are other extensions to this framework. So the idea of this whole thing is that it's a general framework to think about turn taking. It's not the specific solution I've described that are important. It's just a way to think about it as this transition finite state machine, and plugging in decision theory on top of these states and actions. And possible extensions include changing the topology of the finite state machine itself, particularly if you have more than two speakers, then obviously you're going to have a different structure. You can change cost functions. As I explained during the talk, these functions are fairly simple, the one I described, and you can maybe do a better job. The ideal thing would be to relate the cost functions to user experience. If you have measures, high-level measures of task success, I don't think it's going to relate necessarily highly with this, but user satisfaction might relate more. So if you can get some correlation, some way of fixing the cost of deciding the cost based on that, that would be a much better optimization criterion than the current one. And you can also improve just the probability models you're using. Again, using different features, classification, regression models, and different types of priors. Yes?
I agree with what you were saying with regards to the cost function. That is, if you use user satisfaction.
Right.
But user satisfaction is, I think that relates a little bit more to something that, as far as I can tell, you haven't really discussed much with respect to the decision processes, which are decisions that you make over time.
Mm-hmm.
So far what you've presented seems like a greedy approach, where all you're going to do is you're just trying to maximize or you're minimizing your expected cost, right, for every particular point, but not across a sequence of points. It's clearly, if you grab too much, you know, you're going to upset the user, you know, the cost is going to be greater, right? So have you thought about, you know...
Right, so that's a very good point. So what you're saying kind of leads towards reinforcement learning approaches. So actually modeling this as more like a Markov decision process, where all the actions are in a chain over the different turns.
Not necessarily, so depending on the optimization function, but I mean, clearly what you're not including so far, at least, are even just dependencies between the decisions that you make.
Right, so yeah, so I mean, one way to answer this, one thing I've thought about is, I mean, you can use this machine also to remediate when something went wrong. So I mean, that's not exactly what you're saying, but it's a first step. So you know, when you did interrupt the user, when you did a cut in here, okay, sorry, if we're going from here to here, then you can use this to at least make the right decision then, right? So repair the problem. So you can use this for repair. And what I was thinking, but it's a good point, that it's not embedded in the current decision framework itself. But when you observe these things, you can change your cost structure and make it more costly to have a cut-in if you already had cut-ins before. For example, I mean, a very simple.
Up at the higher level means that you are not trying to understand what user wants and the goal and how far you are away from the goal. So if you see that you do successive user utterances, such a wide digression, you know something is wrong, even though your timing information is not telling you such.
Right. So, well, basically, yeah.
It sounds to me that inherently in your research, you're basically just model an area that where latency is somehow related to a dialogue experience, but there's a bigger picture.
Right. But I agree. But I think that comes from, I don't think that questions the overall approach, but it's more that you will need more complex cost functions and maybe topologies as well. But I think this will still capture a lot of the phenomena, even in more different tasks where, for example, it's not necessarily always good to be as fast as possible, for example, which is what this particular approach did. Right.
No one can knock decision theory.
One argument for the approach I've taken, which is very local in terms of decisions, can come from the conversation analysis work, which can be questioned, but like in the Sachs and Shegeloff, the original turn-taking paper about human-human turn-taking, they actually made it explicit that turn-taking is a local phenomenon that's independent of context. Now you can actually question that, but there's actually a take on turn-taking, which like a theoretical take on it that makes that assumption. So I think that's why it at least works at all, making that assumption, right? Like you couldn't do that optimizing the general flow of the dialogue, like the actual prompt that you're saying, because that wouldn't make any sense. In turn-taking, you can at least work with that assumption first, and then improve over that by introducing more dependency.
That's why I think it would be really interesting to try to apply this model to look at conversation analysis and see if it actually can apply.
Yes, I agree. I agree that would be interesting. I don't think I'll do that in my thesis, but no, that's very good. I wish someone did that. Okay, so I've presented two principled approaches in different ways to turn-taking. First one is an optimization algorithm to get endpointing thresholds. And it showed that dialog features can help turn-taking, particularly semantics if you have them. Now, it might be that on some complex domains, it's much harder to get reliable semantics, and then you might want to rely more on other features. In this particular domain, semantics did help a lot. And second, I proposed an approach based on the finite state turn-taking machine that models turn-taking and captures most phenomena, at least in the dyadic conversation, in a fairly standard state transition way. And because of that, we can use that as the basis of what I call the dynamic decision process model, which is based on decision theory to make decisions, turn-taking decisions at every point, based on our belief on what state we're in and the cost of the different actions. And I showed examples of two applications for endpointing and bodging detection. I have actually 2 slides on how that could all fit, or I could all fit in MSR. So first, let me talk about my general research goals. I mean, this was specifically about my thesis work, but in general, what I want to do is improve human-machine interaction. Human-machine interaction is really where I want to be, and improving it by designing models that can learn, and they can learn either from, in both cases, from data, but either from previously collected interaction data that you have, or even better, through new interaction, or both. I mean, you can start from something collected like I did in this particular work, and you can, again, because this is unsupervised, you can actually let it run and tune it, because the user behavior might change once you change the behavior of the system, and so having the thing stay unsupervised actually helps it do online learning, continuous learning. I didn't completely implement the online version of this, but there's no reason it wouldn't work. And also the other aspect I'm really interested in is leveraging high-level task information, whatever the task may be, to optimize core technologies. It's like being at the interface between core technology like speech recognition, or in other domains, information retrieval, etc., and an actual task you're trying to do with it, like dialogue in the case of speech, or other like web search in the case of information retrieval. So in terms of domains of application, to relate to the reason I'm here these 2 days, first for situated interaction, the work that's done in Eric Horvitz's group, well, turn-taking itself is, I believe, crucial to realistic dialogue systems, the kind of systems that they are working on in that group, something that you want to be much more aware of the environment and much more like lead to much smoother interaction with the users and natural interactions. I think that requires to have a good turn-taking model. Whether it's exactly this one or not, that's a separate question, but I think it does need it. And it's kind of a natural extension to the finite state, I mean the whole approach, to multimodal, potentially multi-participant situations. So you can grow, build on top of this and grow the state machine and change the cost structure, etc. For web search, it's not as directly an extension, but it still fits within definitely within my general research interests, in the sense that, well, particularly with Kwan-san, the idea is to take interactive search as a dialogue, frame it as a dialogue between the user and the machine, and that. Given that, it's very interesting to me to exploit, again, to relate these low level and high level, to exploit information on search behavior you have through the interaction to inform the core technology, information retrieval algorithms. And so I think these are the 2 ways both of them would be very interesting to me, actually, to pursue within the context of MSR, at least in the near future. Okay. Sorry, I didn't have a thank you slide. Thank you for your attention.
So do you think for multi-model application, taking less important or more important?
I think it's different. I think it depends also what kind of multimodal interaction, multimodal application. If it's so, multimodality probably is not the big factor. If it's multimodal but not at all human-like, like multimodal because you have a map and you can speak to it, then it depends. What you have to construct a new model of what it is to take turns of what is the interaction. So I think it's important. Yes.
The other way, multimodal addresses the input side. How about the output side, the multimedia?
Right.
In that case, your communication channel between the system and user is much broader.
Right. So basically, you have something where you might have several floors. I mean, there are different ways of modeling that, right? But instead of having a single, if you're using just speech, you have a single channel, and so that's why the floor is there, because you can't easily share that one.
Now,
right.
But what if you have a very high bandwidth communication between user and system?
Right. So I think it leads to a different model of what the floor would mean. I don't think it removes completely it, because it's not infinite, right? At least because the user is never going to be able to process an infinite amount of information presented to them. So you still have constraints on it. They are not the same as just a speech-only conversation kind of
Well,
thing.
we do turn-taking is generic to all human-machine interaction.
Right.
The question is the way you approach turn-taking in your research. You have focused a lot on the temporal information that is derived from speech. The question I was asking is, in the multimedia environment, how important that temporal aspect is. Is that particular to speech interaction, or is as important in the multimedia presentation?
It's potentially, I don't think it's just because of speech. It's potentially as important depending on what kind of multimedia presentation you do. Right, but how you combine the two. So if you're talking about like static web page that has different elements to it, for example, then you don't have, like within this context, turn-taking, if it's not directly time as in millisecond problems like I'm talking here, it's at least about the sequence of things. Right. So, but as soon as you have things happening in sequence, like basically, you do have, even in any application, you do have the system and the user taking turns in some fashion. Not necessarily strictly one at a time. It's actually more interesting when it's not. But you still have turn-taking happening here because of the transition. There's still a temporal transition, is what I mean. There's a cycle. And so that still, even if it's not, like optimizing the thresholds like I did in the first part, it's not going to apply directly, obviously, because you don't have this specific problem. Now the second approach is more generic and can actually lead more, because you can have these transitions, this state machines, they can apply.
The question is that in the case, let's say in a web search, the latency or the duration of the session. How important is that? I mean, in this vocal dialogue system, obviously there
Right. Well, that's a good question, actually. How important is that? I think it's not working at the same scale. Now, is it not important at all? Or
maybe even, it's more important. Getting my dialogue flow accomplished more important than
Sure.
how long does it take.
Now, right. Now, how does the way the turns are taken influence that aspect? Is the challenge, I guess.
We have time for one more question.
Yes, Tim.
Just your thoughts on if you were to work on web search as a dialogue, how would you approach this problem?
That's a good question. Well, so briefly, I mean, I just had a discussion with Kwan-san about this kind of issues. But so the first thing, given what we know about dialogue, like human dialogue, would be to structure the problem, because if we want to approach it as a dialogue, I think that introduces some kind of structure. So you can be in a state, get some input, make a decision, and move to a different state. But you need to define what these states are. And the plain old information retrieval paradigm doesn't have that. It's very specifically unstructured, actually. And so you need to define some structure, either by clustering documents, or there are already some approaches to that, and then moving around. But there might be other ways to do it, actually, better ways to do it, maybe.
Or just like you can use that application detecting margins, you'll be able to detect when you are actually required, needed to get some information from the web, so you can make it more efficient. So you just don't have to try to present a lot of information where user was not ready.
That's an interesting, definitely interesting point. Like, can we have the system to be more proactive by being more aware of what's happening in terms of floor, even if the floor means something else in here.
In the case, some of the case in search is already happening. As you type in query, it's
for example,
no suggestion, right? But the time scale there is actually much smaller than the speech.
Yeah,
it's as you type, every character you type is trying to reformulate your suggestion, and so the latency and all the timing information.
It's completely different scales. Yes. No,
So you don't need to respond when you don't have enough information for them. Right? That's the one strategy.
I know my own thoughts.
You guys are all in the field. Why don't you use your one? So with that, let's thank you.
Thank you.
And thank you everybody for coming.